Great. So there are two pieces of DeclareDesign that we want to share with you today. The first is a language for describing research designs, and it's in 4 parts: a model, an inquiry, which is a research question about that model of the world, data strategy that yields data through sampling, treatment assignment, and measurement, and an answer strategy that takes the data that results from that and provides an answer to that question. And we call this MIDA. The second is, how do we go about choosing a research design? How do we choose a good research design for the question that we've posed? And so we'll show you a 3-part algorithm for doing that starts out with declaring or defining your research design in terms of these 4 components in code. The second is, by virtue of the fact that we've declared them in code, we can run our study over and over again in a simulation, in a Monte Carlo simulation, and assess its properties, things like power, but also bias. And then third, if we don't like what we find from that diagnosis, we can redesign. We can change the parameters of our study to improve the power, to reduce the bias, and to select among a set of feasible designs, which is often what we have to do before starting out with our research. So I'll talk about the language, and then I'll kind of hand over to McCartan to talk about the algorithm. So a design declaration is in these 4 parts. The first part, I think, is the kind of hardest to grok. It's the model. That's a word that means many different things. What we mean by it is a set of suppositions about how the world works. So what are the set of variables that matter particular problem, and how do they interrelate? What are the treatment effects of a treatment on a set of outcomes? How do those treatment effects vary by pretreatment covariates? What are the pretreatment covariates that exist, and what are their distributions? How do we think the world works, and how do these variables interrelate? The second is this inquiry, which is really your research question. This is always a function of variables in the model. So your inquiry might be, what is the average treatment effect of some treatment on a particular outcome? And so that's a function of 2 variables in the model, which are the treated potential outcome and the control potential outcome. It could also be a descriptive inquiry, something like, what is the average support for Hillary Clinton before the 2012 election? And that would just be a function of 1 variable. The third is a data strategy, which has 3 components: a sampling strategy, which is how do the units come to our study? The second is treatment assignment. What interventions do we randomly assign or non-randomly assign to those study units? And third, measurement. What are the outcomes that we measure, and how do we measure them for those units? The last part, the answer strategy, is how do we take that data and produce an answer, as well as an assessment of the uncertainty in the answer. So this is a linear regression with pretreatment covariate controls, where we use HC2 robust standard errors, and we pull out the coefficient on the treatment effect as our estimate of the true average treatment effect. So these are 4 components of this design declaration. In the book, we situate this in this broader process of research design. So we have these 4 components of the design. Those are all in control of the researcher. Those are what you select when you begin to research. But what they're trying to do is to mirror a reality, a set of things that we don't get to observe. So of course, there's the real world. We're going to try to approximate this and learn about it through a model. It's going to be an approximation. We have an inquiry, which is a question about that real world, but we don't get to observe the real world, and we don't get to know the true answer, for example, the true average treatment effect. And then we can select our data strategy and answer strategy, and those are going to result in data and then estimates that are a function of things that happen in the real world and these choices that we make about our research design. So we want to mirror the theoretical world through our model and inquiry, and then we want to get data that provide information about that real world and about that true estimate. We want to choose a really good research design that does a good job of mirroring the model and getting estimates that are really close to that true answer. But we face a problem, which is that we can't observe that true model, and we can't observe the true estimate. And so a lot of what we're going to focus on is how to approximate that model in our design, and then how to simulate from it. And so we're going to, because we don't have access to the true model and this true estimate, we're going to have to approximate them. And we're going to use this Monte Carlo simulation procedure that McCartan will talk through to try to create a set of simulations that simulate the world, and then we can compare the estimates that we get in our simulations to the conjectured estimates or the conjectured average treatment effect, for example, under this set of assumptions about the world. So we're going to do that using this R package DeclareDesign. Here we're going to take from you all of your conjectures about the world, your question or inquiry about it, your detailed data strategy and detailed answer strategy, and then we're going to run your simulated study under these assumptions over and over again and get a sampling distribution of your estimates of the average treatment effect and also the conjectured estimates, the conjectured average treatment effects under these assumptions. So just to give you a sense of where we're going to go by the end of the day, this is a declaration in DeclareDesign of a 2-arm trial. So we're randomly assigning units to a treatment group and a control group. So we have each of these 4 components: the model, the inquiry, the data strategy, and answer strategy. In the model, we define 100 units. These are our study units. We're just going to assume that we're going to run an experiment on these 100 units. Maybe they're students in our class. We don't really care where these units came from. We're not interested in generalizing here to a broader population. We're going to define 2 characteristics of each of those 100 units. The first we'll call X. This is a pretreatment covariate that we measured in a baseline study. This is just a binary variable, so we're going to use the R binom function in R, and with a 30% probability of getting a 1 to use later in our design and our blocking strategy. Second, we're going to imagine that our outcome is also going to be a function of just unobserved heterogeneity. And so we're going to represent that with U, and we'll use R norm to generate a normal distribution. Then we have our potential outcomes. This is how all of these variables fit together under our model. So here we're going to say that Y, our outcome, is a function of Z, which is the treatment variable that we're going to randomly assign. We're going to assert that there is an expected effect size of 0.1. Because I've set up U to be R norm with a standard deviation of 1, this is a 0.1 standard deviation effect. This is not something that we necessarily need to believe coming into an experiment. Of course, the object is to learn what the estimated average treatment effect, not to assert it. But we have to make some conjectures about what that's likely to be in order to understand how good our design is. And so we're probably going to want to make more than one conjecture. And so McCartan will show you how to look at how good the design is across a range of different expected effect sizes. We also have an effect of X, that pretreatment covariate, and an effect of U, which is that just unobserved heterogeneity, other things that matter for the outcome. The second piece is the inquiry. This is the average treatment effect. And so because we've declared this model, there is data that can come out of this. And so our inquiry is a function of some variables in that data: YZ1, that's the treated potential outcome, and YZ0, which is the control potential outcome. Now, you don't see those in the model, but that's because this potential outcomes function is a helper function that takes a formula that describes the outcomes Y as a function of Z, which is the treatment variable. And so it's going to generate 2 different variables. One is YZ1 and one is YZ0. And then you can use those and take the mean difference to get the average treatment effect under this set of assumptions. So that's our inquiry. Then we have a data strategy. This could typically include sampling, treatment assignment, and measurement. Here it just includes treatment assignment because we only care about these 100 units. We're going to use block random assignment. This is from our randomizer package. We're going to block on this pretreatment covariate X. So we're going to run a little mini experiment within people who have X equals 0, and another little mini experiment among people who have X equals 1. In the first one, we'll set 10% of people to get treated, and in the second, we'll set half to get treated. Then we're going to measure outcomes. Here it's very simple. We want to reveal the outcome Y from the potential outcomes. And so we use this little helper function, which is basically the Gerber and Green switching equation, which takes the potential outcome for the condition that you're revealed it. So if you are assigned to treatment, we're going to pluck out your treated potential outcome, and that's your observed outcome. If you were assigned to control, we're going to pluck out your control potential outcome, and that'll be observed outcome. So that's what reveal outcomes does for you. Finally, we set up our answer strategy. In this case, we're going to use LM, linear regression. We're going to use classical standard errors and not robust standard errors. This is the formula which tells us that the outcome is Y. and we're going to predict it using Z. An important part of the answer strategy here is this is where we're going to link the estimates that come out of this to our estimands, which come out of our inquiry. And so here, our inquiry is the average treatment effect. And here we're going to pull out the coefficient from Z, which is our estimate of the average treatment effect. And so that's how these two are linked together. And then we'll be able to create a diagnosis of this in which we can compare our estimates to these simulated average treatment effects. So this is a design. This is how we do the first step of our algorithm for selecting designs, which is to declare them in code. The reason we're going to declare them in code is because then I can take that function, that design that I just showed you, I can actually run it. I can get out data from it. I can get out simulated estimates based on that data, and I can get out a simulated estimand, or that true average treatment effect under those assumptions. So we'll use that to do what we call diagnosis, which is running that over and over again through a Monte Carlo simulation, and then calculating summary statistics of those sampling distributions. So saying something like, what is the average estimate that we get out of this design? What is the average estimand that we get? What's the average difference of them, which would be bias? The last step of the algorithm is to redesign. So we're going to get a number for what we think the power of this design is, what we think the bias is. And we may not like those. We may find that we're underpowered, or that we have some bias because we didn't account for the fact that there are different probabilities of assignment with, across blocks. So we might want to change the design through redesign, redeclare, diagnose again. And we may also have a set of 10 designs that we have in mind that we want to choose among. And so we could redesign across all of those 6 designs and figure out which one is optimal under our funding constraints, for example. So that's kind of the opening here. I'm going to turn over to McCartan now, who's going to do a demo of using a research design. Then you're going to try that out in our Markdown document in groups for about an hour. We'll be jumping in and out to help. Then we'll come back together, and I'm going to do another demo of getting more into the weeds of declaring a design. So we'll walk through different versions of a 2 and then a 3-arm trial. Then we'll break up into groups and we'll work on a second practicum, which is running through a set of design declarations. And then we'll come back together for the last 10 minutes to kind of talk about how you can adopt DeclareDesign and how we can help you do that. So I'll hand it over to McCartan.
So first of all, Graham, I think we have 2 hours, not 3 hours.
Yes, 2 hours.
Okay, so let's rejig the numbers on that last slide and send them into the chat with 2 hours rather than 3 hours. So we might have to shorten some of the practicums, but we'll make it work. So great to see everyone. What I'm going to do is I'm going to go through a kind of a live demo of using a design. And so my thought here is we're going to give you the kind of the good stuff first, in the sense that we're going to sort of assume you have a design and then what you get out of it. And that involves using it for when you're implementing, using it for helping think through how you should be designing things, and also for diagnosing and this end of things. And then the second practicum and sort of live walkthrough is around creating the design. So for now, I'm actually going to abstract a bit away from creating the design and go into using the design. And I'd also say, I think we're a small enough group, that if people are confused or want to, raise a quick question, just speak. I think it should be fine. So I have here our studio. I've got my code here on the left, and I'll be getting some output here on the left and some output on the right. I'm using 3 main packages: the DeclareDesign package, the design library package, which has got a set of kind of pre-designed designs that make it very quick to generate designs. I'm also loading up tidyverse here, and the reason for that is you'll see some of the code uses sort of piping, tidy piping, which makes things a bit neater. And then I've got a couple of packages here that are just for making nicer output. So I'll load all those. And then what I'm going to go through, the commands I'm going to go through. Oh, I should also say these slides, as well as the exercises, are on the web page that was circulated. So if you want to, you can open these and follow along as we're doing it. There's a slight difference between these ones and the ones on the website. I think the RMD on the website includes a display command that produces slightly nicer output, but the core code is all the same, and you can run it straight through. So I'm going to go through the idea of drawing data from the design. Once you have a design, you can draw data. You can use the design and look to see what are the estimands implied by this design, or what are the estimates I get from this design. You can also use the design to implement your research. So you can use the design to draw your treatment assignment, for example, or to actually run your analysis after you get the real data. And then you can use the design to simulate the design and use the simulations to do diagnosis, which is kind of the most important part of this, because that's what tells you whether your design is doing what you hope it is meant to be doing. And then you can use that to redesign. So I'm going to go through those sets of steps. So first of all, get your design. So the command here I'm using to get your design is I'm creating a design. It's on the left of this arrow, so that's being created. And I'm using the design library to generate a two-arm design using a two-arm designer, right? So that's just a function in the design library. If I run that line of code, I now have this is a design as an object. You know, one thing we really like about this whole setup is that designs stop being, you know, lots of documents, you know, and scripts and things all over the place, a whole, you know, collection of things, and become a single object that you can interrogate. And so now I have one from that one line. I just point out that when I had that sort of designer there, there are various arguments I could have provided, such as the n, the ATE, the control mean, and so on. Right? I could have specified this design in particular ways. For now, though, I just took the default settings and chose a design like this. Okay. So I now have a thing in memory called the design. And actually, if I just enter that, if I just enter this here, it will run the design once. It goes through and runs the entire design. Right. So once you have a design, you can just enter it, and then it'll go through what's happening in this design. So this design's got a first step, which is declaring a population, similar to what Graham showed before. And you can see the arguments, there's an n, there's a u0, and so on. And then it creates this data, and it says what the variables are. Then step 2 is potential outcomes. It has the code there, and it produces it, and so on. Adds variables, does a draw of the inquiry, does a calculation, does a draw of the assignment, creates y, and then implements the analysis, right? So that's actually a single run through. So that the fastest way to figure out whether you've defined or declared the design correctly is just to run it and make sure it goes through from beginning to end, right? If something goes through from beginning to end, you're already in a very good place. Okay, so that's all I needed for a simple two-arm design. And I could have chosen more features for that, but that's it. Once I have a design, what can I do with it? Well, the first thing that's a very nice thing to do is to look at some data. So I'm doing data, I'm defining this thing data using draw data. Okay, so draw data is just saying, okay, if you say you know how your conjecture, you have a conjecture of how the world works, that means you've got a conjecture of what kind of data you're going to be getting, right? Given your data strategy. So here's a draw of data, and what does this look like? And look at this data, head data. I've got an ID assigned. I've got a couple of shocks here, U0, U1. I've got your outcome under control, your outcome under treatment. I've got a particular assignment, Z. I've got a realized outcome, Y. Okay, so that's the structure of the data. You know, I can see what does this data set look like. There's dimensions. There's 100 rows in here because we've assumed an n of 100 rows, and these are the variables I have in here. And you see it should be behaving well in the sense that so the actual outcome y here should be one of the potential outcomes. In fact, in this case, it's both of the potential outcomes because we've assumed a zero effect, right? If you assume a sharp zero effect, it is indeed both of the potential outcomes. But in general, hopefully, it'll be one of the potential outcomes and be the one corresponding to the treatment condition. Okay, so that's how data is looking. I might also check, is my assignment working correctly, right? So what is the distribution of Z look like, or Z, XYZ. It's 50-50, right? So that's what it should be. That's a complete random assignment. It should have exactly 50 in treatment, 50 in control. Good, that's working fine. Okay. I can also now, if I haven't fully figured out how I want my analysis to be, with my fake data, I can just run the analysis sort of live and see, is this kind of working the way I want things to work? So here's an example. I'm just going to run a model using this particular data generated, right? And I can play with different models and see, is this the right kind of model that I want given the data? So that's a very handy thing to do. First thing that declaring a design does is gives you the kind of data you want to be able to analyze. And often you only get clarity about how you analyze things once you have the data at hand. Okay, so that's examining the data. Now I can also say, well, what are the implied estimates? Okay, one thing we kind of like with this framework is it forces you to say what your estimand is. Your estimand is the answer to the inquiry under the model. So given the model or the world you've imagined, you have a question you're asking of it, the estimand is the answer under the model. That's the thing you're trying to estimate. So when you draw estimands, it says here the estimand is 1. Just if that's the number you're aiming for here, right? It's a nice round number here because we've assumed constant effects. Okay, so draw estimates. I'm going to draw estimates here. That's an example of the set of estimates you might get. I might draw again a new set of estimates and so on. Every time I sort of draw estimates, it's drawing a new data set from this design and getting estimates. Okay, so I can do that. They're going to be new every time. I can draw assignments. So this is now a slightly different operation. Now we're saying, say I have my design and I go to the field and I want to now do assignment, right? In the olden days, you used to have a separate script for doing your assignment and doing your pre-analysis plan, you know, and your analysis and so on. The idea here is when you've declared your design, you've already specified what your assignment procedure should be and your analysis approach will be and so on. So that's already in the design. You can now just go to the design and draw the assignment. So here's an example of one assignment here. So that's one assignment. That's another assignment, okay? So every time you draw assignment, it's going to pull Z afresh every time. Okay? As an aside, it's not going to recalculate Y. You're not asking it to recalculate Y. You're not rerunning the whole design. You're now pulling an actual assignment, Z. That's what's going on there. Okay. Before I showed an example of where you're drawing estimates, right? You're saying, okay, this is my design, what my estimates look like. And every time I drew the estimates, I got a different set of estimates, right? But I can also say, oh no, I actually have my data. I don't want to write any new analysis code to do my estimation. It's already in my design. So I'm going to say, if I have my data, can you please give me my estimates? Right, so I just get my estimates given my design and my data. I don't rewrite my analysis code. Okay, so I get my estimates for this particular data set. And now if I run this again, I get the same results, which I should do because I'm not redrawing data now. Right now I'm using actual data we've gathered and I'm imagining I can use my design to run my analysis. Okay. So far we've kind of looked at you can once you've declared your design, you can get data, you can check that the data has the right sort of structure you thought it had, you can work through and see how different estimators might work with it. You can ask, what do the estimates I would get from this data look like? What do the estimands I get from this data look like? And all of those are useful things to do to try and get a sense of whether the design is capturing the kind of process and worlds you care about. And then in this next phase, we're saying you can then use it for implementation. Okay, that's going on with implementation. Okay, the next set of things are around simulation and what we call diagnosis of designs. So when you simulate a design, if you remember before I said, if you type design, it runs through the design. The design is constructed to be a thing you can go through from beginning to end. It follows a pipe kind of structure. It goes from beginning to end, from how the world is to your ultimate estimates. So when you simulate a design, you do that same thing many times, right? So here, let's see, maybe I'll get a nicer display here. So here, I simulated the design. I did it 3 times. We recommend you do it many times, a couple of 100 times, but you see it's very rapid. It did 3 simulations of the design, which means it generated data 3 times, it generated the estimate 3 times, it generated the estimate 3 times, and we're seeing here a distribution of estimates that we get, right? For each time we run it, we get a distribution of estimates, okay? And that's what's used for diagnosis. So when we see a distribution of estimates, we can say, is that distribution of estimates, is that something that's centered on the truth, right? Is it a good distribution of estimates, right? If it's centered on the truth, it's unbiased, and that's great. So once we, yes.
Just one quick question. So when we do this, the population is also redrawn. Just this is clarification.
Yes. So, the basic simulation,
right?
You go from the very top right down. So you're redoing everything every time. Right?
So if it says R norm in the model, it'll
redraw everything.
Got it.
Yeah, everything is redrawn. However, it's a slightly advanced topic, but you can set the simulations separate for every step in the design, right? So you can actually have, say, 10 draws of the population, and for each draw of the population, have 5 draws of samples from that population. And for each draw of sampling, interesting, you can take 100 different random assignments, right? And it'll go through all of those branches of things. So you can do all that if you want to. So if you're interested only in the uncertainty, I'm guessing you're asking, if you're interested only in the uncertainty from a randomization, right, you can fix the population and branch out at that point, right? But the normal thing we do is just have a single number here and go from top to bottom multiple times. Yeah. Okay. And once we have that kind of distribution of what sort of effects you're likely to get, what sort of estimates are you likely to have, what are your, so alongside here, we also have your distribution of confidence intervals, your distribution of p-values. That's the information you need to answer questions like, what's the power of my design? Which is, what's the probability that my p-value is small, right? Or to ask, what's the coverage of my design, of my estimator, which is, what's the probability that the truth is going to be inside these here over repeated draws between the confidence low and confidence high, right? For a given truth. Okay. So then when we diagnose the design, so now we're going to do it 100 times. So this will take slightly longer. We're going to regenerate the data 100 times and do the estimation 100 times and so on. But that's how long it took. So not that bad, right? For kind of 100 simulations of the design. In this case, we estimate no bias. There's a nice kind of thing. We also estimate our root mean squared error. So although it's unbiased, that does not mean it's right. Okay. So what the root mean squared error will tell you is get a sense of how wrong you are on average, right? This is saying how off you are from the truth on average. So it's going to, you might be on average, you're going to get the right thing, but you can be wrong every time. And what the RMSE is getting you is how wrong you are every time. The power, which in this case is fabulous, it's significant every time for this particular set of assumptions we have. The mean estimate and mean estimand, so are 1. We've got a standard deviation of the estimate. What's interesting here is we get to directly compare the average standard error that we calculate with the standard deviation of the estimates. So this is going a little deep into frequentist theory, but that's exactly what the standard error is actually targeting. The standard error is trying to figure out the standard deviation of the sampling distribution of the estimates. And you never really see those two things side by side, but here you see them, and they're tracking really very well here. And that's kind of nice. There's a couple of other things here. Those are the things we call the diagnosams, the things that you diagnose, or the things that tell you whether your design is good. And this particular design is doing very well. It's great. But the warning is it's doing great given what you've assumed about the world. It mightn't do great under other assumptions about the world, right? But that's a question you can then ask of a design. You can say the model is different. Then how good am I in terms of bias or power or something else? Okay. All right. So the next idea here is the idea of maybe just I'll pause there for a second, see if there are any more questions, because that's most of the kind of how the flow of a design works.
I'm trying to understand the difference between when we would use simulate design versus diagnose design.
Yeah. So in general, so what diagnose design does is it first of all simulates the design. So it will actually call this function, the simulate function. It'll do this. Call this function 100 times. Create a simulations data frame that looks a lot like this, and then apply a set of summary statistics onto that. Okay, so for most purposes, you don't bother simulating, you just do this, right? For some purposes, you actually want to, look at these numbers in ways that aren't kind of, canned, and it's kind of useful to see this. So if I were interested, we've done things like we're interested in publication bias, so you're interested in something like, well, what is the average effect among studies that are significant at some level, right? You can define a diagnosam and just do that here at this stage, but it's really easy to get your simulations data frame and just look at that distribution, and get an understanding of how things are working, and then you might integrate it into the diagnosis. But in fact, one of the things that's produced by diagnosed design is a simulations data frame. So you can do that. Okay, so the short answer is you probably wouldn't have to use this, and you might go straight to diagnose. Okay, great. So what redesign is, it's one of the most useful, but I'd also say most treacherous parts of DeclareDesign, right? So the key idea here is you can take a design. So you can take one person's design and say, oh, I want to design a lot like that. Just I want to be a little bit different, right? I'm going to take the design and I'm going to alter it in some way, right? Now you can always just take their code and change their code and go from scratch and write your own design. That's not a bad way to share designs, right? But often you might want to kind of compare 10 or 20 designs that are quite similar in some sort of way, and you want a neat way to make modifications of those designs. This function here, redesign, lets you take any design and alter any elements of the design, any arguments of the design that are called by DeclareDesign functions, right? So in this case, I'm going to take this design. I'm going to put a control mean of 0, a treatment mean of 0, and a row of 0, right? So the design has a control mean built in, a treatment mean built in, and a correlation between the treatment and control outcomes. I think the default is 1, and I'm now making that a 0. So I'm changing 3 aspects of this design. And I can do that because if I look at the code of the design, those are all elements in that code that are called by DeclareDesign functions. Okay, so here's a new design that has these features. I'm going to create it. Normally, you'd probably rename this. This is design 2, is a variation on the original design. Okay. So if I take a design, I can then redesign it and then diagnose it. But when I redesign, I can change actually not just multiple arguments, but I can give various arguments multiple values. So what I'm doing here is I'm taking the original design, I'm giving it a control mean of 0, treatment mean of 0, and now I'm letting the row change, the correlation between potential outcomes change over 3 different values, right? So in fact, what I'm doing here is I'm using this one command to create a list of 3 designs. And now I'm going to diagnose all 3 of those designs at the same time. So this will take a little bit longer because it's now doing that diagnosis simulation over each of the designs in this list. I'm going to produce an outcome over all of those designs. So, and the outcome output looks like this. I've got my designs listed here. It says how they vary, these designs. So it reports back the things I had varying here, right? So you can see here's the design if it's row -1. Here's the design of row 0. Here's the design of row 1. And then I can see how they behave differently under those different designs. And what I'm seeing here is bias is unaffected. There's actually a little thing there for simulation error and so on. Power is pretty similar. The main thing that actually changes is the coverage. It's kind of a technical point. The coverage is more or less correct for one design. The row is one design, but off for the other two designs. So it's conservative for the other two designs. What I could do, and then the exercise is we ask you to do something similar to this, but varying the n. So I wanted to design with 100, with 200, with 1,000, and see how things change when the n changes. Or we could vary the estimated treatment effect, your guess the treatment effect, and see how the design changes with that. Okay. All right, and it's this kind of thing here, the diagnosis over multiple designs, that we mostly use when we're trying to figure out what's the right design for me, right? And that might mean what assumptions about the world do I think are plausible, but also what features of my sampling strategy or my assignment strategy or my estimation strategy are getting me better outcomes, right? You get that answer by comparing the diagnosis over variations of a design, right? That's kind of the go-to approach. The last thing, I won't go through it now. The last thing I'm showing here is you can plan a wonderful design, and then you go to the field, and when you go to the field, things work out differently, right? And your design actually has got fewer participants than you expected, or you end up maybe doing your analysis but differently to how you expected, and so on. Things can be different. What you can do is you can come back afterwards and say, okay, I have my original design, I've got my actual implemented design, and I can compare those two designs. So the code here is comparing the original design with 100, n is 100, and the final design with n is 50. And when you compare diagnosis, it tells you, are those designs different in important ways? Probably should have had that. I'll just put it running and then come back to it. Okay, that's the walkthrough. That's the kind of set of uses of a design that I wanted to cover. Oh, so here what we have here is we've got our designs. We've got a comparison between design 1 and design 2, and we're seeing how do they differ, and I think we should be seeing the difference between them. So we're seeing big differences here, for example, on the standard error you get from these designs, for example. Okay, the tasks we have before us are. So I just wanted to check one thing. There's one thing that's been confusing me throughout this. Okay. So the task we have before us is we're going to make a simple factorial design using a 2x2 designer. We're going to print the code of the design. See how it looks. So let me just show you print code. If you have a design, we say get design code. We get the output of the design. It's
probably a little bit below if you scroll down the markdown.
Oh, that's not displaying right here. Not sure about that, but anyway, here's what this actual design code is looking like, which normally is coming out when you do get design code. So we're gonna do a 2x2 factorial design. We're gonna print the code of the design. We're gonna draw data, make sure it has got the right structure of the data, make sure we believe it. We're gonna redesign it to make it a slightly more interesting set of potential outcomes. and then diagnose it, see if it's behaving the way we'd like it to behave, understand whether it's got good power. And in particular, we're going to look for power for the interaction term, which is something that you can't get from standard power calculators, for example. And then we're actually going to go through an exercise and think through what n would we need in a design like this in order to have good power. Okay, so that's the last part of this exercise.
Okay, so I'm going to I'm going to start out with a two-arm trial. So randomizing treatment and control, and I'm going to try to walk through each of the steps of the declaration kind of slowly. And the way that I like to declare designs is to start out with each step and then draw the data. And if I've gotten to some estimation, draw some estimates just in the way that you were doing there. So at each step, you can kind of start to see what you're building up. And so I'll do that as I walk through. So I'll start with the design here. I want to start with a model. I'm just going to choose to have 500 subjects here. And just to keep things simple, like the design that I showed you at the beginning, I'll include some unobserved heterogeneity here that has a standard deviation of 1 so that I can benchmark my effect sizes against standard deviation effects. So I could go and look up what is the standard deviation effect size in this literature in the past, and I could plug that right in. So I'll add some potential outcomes here. In the ones that we've done in that design that I showed at the beginning, there are 2 potential outcomes, and so I'll show you what that looks like here. So we have a variable y. I have an effect size of 0.1 standard deviations, again because of deciding on a standard deviation of 1. And so now I'm going to show you when I set up a model here. If you only have a model, you need to add null to it, which is kind of strange. But that'll let me draw some data from this. I'll draw data from this design. Live coding is terrifying. And so here, as McCartan showed before, we have YZ0 and YZ1 and U. And so I can see that these are related to each other by a shift of 0.1. So we move from 0.65 to 0.75. So my effect size that I set up seems to be working. You're not restricted to just 2 potential outcomes. There's a conditions argument here, 2 potential outcomes, where you can just tell it what conditions you want. And so here we haven't decided on what our assignment procedure is yet. And so we can imagine lots of different potential outcomes from different treatments that we might be considering running. And so the way we do that here is to have, this is the default, where Z is the treatment variable, and then we have 2 conditions, 0 and 1 representing control and treatment. But I could add a third one here that would be a second treatment. And so here I could say there's a 0.1 standard deviation effect for the first treatment, but the second treatment is going to have a much larger effect of 0.25. And so I specified those 2 different treatment effects. They still share that unobserved heterogeneity. And so when I run that, then I'm going to get 3 potential outcomes that start out with that same control potential outcome and then add either 0.1 or 0.25 to them. So just to give you a sense of that. So I'm going to go back to this simpler one here. So now I have a model set up. And I want to declare my treatment assignment. So I'm going to declare assignment. I'm going to ignore sampling and just assume that we're just interested in an experiment among these 500 units. So I'm going to just use complete random assignment, keep things simple. So with complete random assignment, we just need to tell our sample size. And one thing I wanted to highlight here was that capital N plays a special role here. We call it magic N. And it's because it knows what sample size you have at all times. That's really handy, so you're not typing out 500 lots of times. And it's especially handy when you have multi-level data, where you don't necessarily know in advance what the sample size is of how many people there are in village 25. So here, because I set N equals 500, when I create U here, this unobserved heterogeneity, it knows that N means 500. And again, when I'm down here in declare assignment, I need to tell complete random assignment that I'm going to assign 500 people, but I can again use magic N there And then I can tell it that I want to do a probability of 50%. So I'm going to assign half to treatment and half to control. Anytime that I want to measure an outcome, I need to have declare measurement, even if there's nothing kind of complex going on, with no indexing, nothing. I need to use that command that I showed you earlier, which is reveal outcomes, which just runs the switching equation and picks out the right potential outcome depending on whether you're assigned to treatment or control. So I'll illustrate that. We draw data here. So I added two steps there. First, I added a variable z, which is the treatment assignment. So you can see that that has 0 and 1 for treatment and control. And then now we have a new column for the observed outcome y. And this is the switching equation. So y negative 1.486, and that's because this unit was assigned to control. And so it picked out yz0, the control potential outcome. But for unit 2, who was assigned to treatment, this has the treated potential outcome, 0.444, as the revealed outcome. So reveal outcomes just stitches those together, even when you have really complicated potential outcomes, like in a factorial experiment, where you might have two different treatments that are being assigned. It's going to pull out the right potential outcome for the right, depending on what you're assigned. So now we have the treatment assignment, the revealed outcome. Now I just want to set up an estimator. So I don't want to use LM. I want to use, if you read the debate on data colada this week, there are a lot of debate about which form of robust standard errors to use. So I want to use HC3 standard errors because that's what they told me that I should be using. So I'm going to use LM robust, which is our regression with robust standards package. And that has an argument called SE type, which lets you pick from classical standard errors or robust standard errors or clustered standard errors. So now I can draw not just data, but I can draw estimates from this. So if you do draw estimates on this design now, it's going to run LM robust on the data. So it's going to run the data, which is the model, the assignment, and the measurement, create a data set, and then it's going to run LM robust on that. One important thing that I want to note here is I want it pulled out one estimate from that regression. If I just ran that regression, I can just run that myself. Sorry. I can just run that myself. There's two rows here. There's the intercept and the coefficient on z. And so implicitly here, this is picking out one of those coefficients. So the default here is to pull out the first non-intercept coefficient. But you can set that, and you'll often need to if you're doing multiple treatments, for example. Okay, so I've got a design. I have a model, a data strategy, and an answer strategy. So now I want to diagnose that design. So put that in here. So I can run that 250 times. And here we can see that from this design, I can get some diagnosins. I can get the power, for example, because that's just a function of your answer strategy. I can get the mean estimate, but I can't get things like bias and the root mean squared error and the coverage. That's because I haven't defined an inquiry for this design. And so there is a mix and match flavor of declare design, but you're going to kind of get what you put into it. So if we want to be able to say what's the bias here, we have to know what is the estimand that comes out of this and what's the estimate, because the bias is the mean difference between the two. So I'm just going to add an inquiry here as the average treatment effect. And again, in the inquiry, this is always a function of variables in the model. And so because up to that step, I had created declare model, and we have those two potential outcomes, yz0 and yz1, I can just take the mean difference between the two. And so now when I diagnose this design, I'm going to be able to get the power, which is the same 0.22, but also bias, the root mean squared error, and the coverage, which is this measure of the quality of your standard error estimator. Okay. We can improve the power here. So you did an exercise where you improved the power. I can do that really directly here by just changing the number in n. So because of magic n, I only have to type that once, and everywhere else in the design, it's going to that's going to pull through. So if I simulate that, that's going to take a second more, but that's going to give me a much higher power. So we're getting close to 80% power here, 0.73. But another thing we might want to do is use the redesign technology that McCartan showed. And so the way to do that is to create your own variable for sample size. It could be called anything you want, n or sample size. I'm going to set that here, and then I'm going to change n to be sample size. So when I run this, it's going to pull that variable. It's also going to allow us to redesign across sample size. So we're going to be able to change sample size as we go. So we can redesign this design, and I'm going to set sample size to be, I'm going to try out, I want to find the smallest sample size that has a sufficient power. So I'll do 1,000, 1,500, and 3,000. When you run redesign, that's going to create 3 versions of this design that have 3 different sample sizes, 1,000, 1,500, and 3,000. And then into diagnose design, you can just put those designs plural, and it's going to run all of those designs again, as you did with the design library. Okay. I'm just going to show 2 more pieces. One is we're often interested in comparing estimators. So this data colada thing had a debate between, had a kind of showdown between different standard error estimators. And so we could add a second estimator here that instead of HC3 had stata standard errors. Only trick here is that you need to label these, because we need to know what we need you to give us a label for in the diagnosis. So in the diagnosis, you can see here, this is just called the estimator. When you have more than one, you need to label them yourself. So I'll just call these stata and HC3. And so when I run that, I'm going to get 2 lines, one for each of those different estimators. And so everything else in the design is held constant, and I'm just going to compare the performance of these 2 different estimators run on exactly the same data each time. And so we can see that in this case, there's not a huge difference because we have a very large sample size. The last thing that I want to show is we're looking at kind of continuous outcomes here, but in lots of social science examples, you want to have binary yes/no outcomes, like did you turn out to vote? There's a number of different ways to do this. I'll show you one quick way to do this. I'm going to change the unobserved heterogeneity so that it uses a uniform distribution. Then I'm going to basically chop people up. If they're above 0.5, if they're above 0, they're going to be a 1, and otherwise they're going to be a 0. And so here in the potential outcomes, these need not be continuous. I can just put in a greater than symbol. And so everyone who's above a 0 gets a 1. And I could express that as using an if else. So here, y is a function of not just z and u, but if you're above the threshold of 0, then you're 1, and otherwise you're a 0. Where we see into kind of your research life cycle, a library of designs that we've been putting together, and some resources for getting help in declaring your own design. So we obviously we've expansively imagined all of the ways that this can help you in your research, drawing from our own experiences using it in our studies over the last couple of years. And I won't highlight them all, but we think it can be really helpful, obviously in the planning stage where you're trying to decide on a specific design, a specific data strategy, an answer strategy. In writing up your pre-analysis plan, where this can provide specific simulated data that you could use to write a registered report, for example, but also after the design is complete. If you didn't declare your design at the beginning, it still may be really useful to declare it and understand what, for example, the minimum detectable effect size of the design for various estimates is. We also think it can be really helpful in trying to resolve disputes between authors and replicators, and getting them onto the same page. What are the set of assumptions that we have to believe, and what are the properties of the design with different covariate, different control strategies, for example. We have in our book a set of research designs from 4 different types of research, defined depending on the kind of inquiry you have and the kind of data strategy you have. So descriptive inquiries that are observational, so things like sample surveys and case studies, experiments that are targeting descriptive inquiries, like list experiments, experiments that are targeting causal inquiries, like the two-arm trials that we've looked at today, and also observational strategies that that are targeting causal inquiries, like difference in differences and process tracing. So I'll just flash up a couple of these just to give you a sense of what this would look like outside of the experimental context. So simple random sampling design that is looking at, for example, the design of a poll isn't going to have, its inquiry is not going to be a function of multiple potential outcomes, but just a variable at baseline. Might have a sampling step as well. So that's an observational design targeting a descriptive inquiry. A more complicated one would be a multi-level model with post-stratification. In MRP design like this, your estimator is where a lot of the action is. And so there's two steps in the estimator. And these are two separate columns, just to be clear. So first you fit a multi-level model. And then second, you make a weighted prediction out of that model using the data. And so in your declare estimator step, you can declare a function that does those two steps in sequence and then assess the properties of that estimation procedure. We have an example of qualitative process tracing that uses McCartan's causal queries package. Here you're setting up a bunch of information about your priors, about what kinds of evidence are going to obtain under different circumstances. A range of difference in difference designs that can help to assess all of the difference in difference innovations that have come out in the last couple of years. So one thing I wanted to highlight here is that we've declared all of our models today as a single level where you just have a number of units and you have the characteristics of those units. But one of the really nice features of our fabricator package in Declare Model is that you can have multi-level data. And so here we have units, and these are nested with periods. And so you can have a country year data set that's created in this way. So you add a level for the units, and then you add another level for the periods. And a lot of the action in these difference in difference models is in the potential outcomes. Are your treatment effects dependent on time? Another observational causal design is a regression discontinuity design. Here, a lot of the action is in the model as well. So we're setting up the running variable and the treatment variable, and using these external functions that are the assumed true treatment and control response functions. And then the other piece that I wanted to highlight here was that we can use that off the shelf. We can take advantage of the fact that there are tons of packages out there for common social science designs, including the Rosio's package RD Robust. You can stick that into Declare Estimator, and we have an example of that. List experiments. Won't go through this in detail, but the potential outcomes include the count of the control items, as well as the latent variable that's a sensitive question. Conjoint experiments are quite complicated, but it does allow you to do a power analysis, of a conjoint. Encouragement designs, where our inquiry is not the average treatment effect, but the complier average causal effect. We're conditioning on a complier type. So I'll kind of leave it there, but in part 3 of our book, we have this design library that is meant to help you get started with most of the common kinds of designs that people are using in political science. So the book is online and free. We also have a set of cheat sheets for DeclareDesign, for randomizer, and for estimator. We have a discussion board where you can post your code that's not working, post your design, and get us to help you declare it. And all of us are teaching on the book at the moment, and so are developing some teaching resources. So if you're interested in that, reach out to us, and we're happy to share them. So thank you so much for joining. We're happy to stick around for a couple minutes if folks have questions.